Hi everyone, this is going to be the KiCAD and PCB design block talk for this semester. So what's the purpose of PCB design? Well, without PCB design, our circuits might look something like this. If you've taken 302, maybe 319K, you've often breadboarded a circuit before. And as you can see here, wires tend to get messy. And then if one wire gets loose, you won't be able to find where that is. And so it just makes debugging really hard and also constructing really hard without mistakes. So this isn't an ideal solution, especially for a system that's as complicated as a solar car. So instead, we can do something like this. Notice how it's a lot neater. There's a lot more solid connections, and you don't have to worry about a trace suddenly coming unloose like the wires. So this is a much better design and especially better for complex systems like a solar car. So PCB design is overall more optimal for our purposes. And so the general process for when you're going about PCB design is first you start off with some kind of design or idea generation. You consider, what do we want the circuit to do? How are we going to get the circuit to do what we want? And what parts do we want to use? So you're just kind of laying out kind of what you think the circuit is going to look like. And then the next step is you're going to actually lay that out in a schematic design tool, such as KiCAD, which has both the schematic and the PCB design part of it. And so you're just going to consider, how is everything actually going to be connected? And then once you have that finalized and verified, then you move on to the PCB layout. And that's when you consider, how is everything actually going to be laid out on the PCB? So what is it going to look like in real life? How's the schematic translate to something in real life? So then once we have that, we ship it somewhere. We send the what we call Gerber files to a PCB manufacturer, who then manufactures the PCB and sends it back to us, where we assemble it, which that's how do we get everything we want on the board. And then finally testing. Does the board actually do what we want it to do? And so in this phase, you often have a lot of cyclical parts to it, where you're going back to edit either the schematic or the PCB based on the test result that you get. So this tends to be the high level process of what PCB design and circuit design kind of looks like. And so this tutorial is just kind of focus on just the schematic layout and the PCB layout part. And specifically using a PCB design software called KiCAD. I know some people also call it KiCAD. I'm used to calling it KiCAD, so I'm going to stick with that pronunciation. So today we're also going to make an example project in which we're going to use this example project, which is a flashing light circuit, a flashing LED circuit, and we'll learn how to make this in KiCAD. It's schematic, and with schematic that you see here, translate that over to the schematic in KiCAD, and then actually lay it out on a PCB. And so we'll start out with the schematic portion first. And so in case you haven't learned this yet, we're going to kind of just go over some common circuit schematic elements that you'll see. So sometimes you'll see like earth ground as these two things. You'll get sometimes the batteries and different voltage sources. Here, you'll see different kinds of resistors, either as the little zigzag or just a rectangle. And then if there's an arrow like this in between, it means it's variable. And then you also have potentiometers that look like that. You have different capacitors. So whenever there's a clear polarity difference, then it's a polarized capacitor. If there's no polarity difference, so it doesn't matter whether the capacitor is flipped or not, there's no positive side or negative side, then it's a non-polarized capacitor there. You have inductors, which are the little loops here. And then you also have different kinds of diodes here, and different configurations to the diodes, and they all have different applications. And then you also have different transistors. You have BJTs, which are bipolar junction transistors, and then you have MOSFETs, which are metal oxide semiconductor field effect transistors. So different kinds of transistors, and you'll see both of them, I think, in the design of a car. And then also op amps, which are fairly useful as well. So operational amplifiers, you do see there's like relays and then logic gates and then some other miscellaneous. So this isn't an exhaustive list of circuit elements. It's just some of the common ones there. So we'll continue with this now. Let's see. We'll continue with this now. And so then we're just going to move on to KiCAD and actually forming a schematic on KiCAD. So let me go ahead and get KiCAD open onto my computer. And so how do you start by making your first KiCAD project? Well, the first thing you do is you navigate over to File and then New Project. And so then you choose where you want to save it. I'm just going to save it here and just call this Block Talk. And then go ahead and save it. And so now you have here, notice how this part changes. If you just downloaded KiCAD, then that part would be blank. And then when you create a new file, this would be populated with it. And notice that there's two different kinds of files here. This bottom one here is the schematic, and this part here is the PCB. And so we're going to start with the schematic. So we'll go ahead and double click that. And so this is what a blank schematic looks like, and it's just completely open and just blank. And so you kind of created your first schematic when you do this. So some important parts to know what it does, this part right here. So this is how you place your symbol by clicking on this little triangle, which is an op amp, and then go ahead and just click anywhere. And so it loads the symbol libraries. Luckily, KiCAD has a bunch of symbols already within its library, so we don't actually have to worry about making it all the time. There is a way to make it, and either in this tutorial or another tutorial, we'll go over how to go about making it. And so let's actually open this up on one screen and then have the schematic that we want to create here. So that way we have it on both sides. And then I can actually pull it up on the website that I got it from. And so it's this LED flasher circuitry. So the first thing that would be good to do is let's go ahead and place this IC here. And this IC is a fairly well-known IC. It's called the 555 timer. And so if you look it up, whenever you're placing components that aren't just general resistors or capacitors are just commonly used ones, it's always good to look at the data sheet to see if there's anything specific that we might want to know about it. Let's say there's a certain package that you want it to look like, or in different things like that. And so, and also the different pin functions, especially when you're going to design your own schematic instead of being given a schematic. It's good to know what each pin does so that way you can connect it properly to what you want to do. And so then it has some ratings. You want to make sure that you don't exceed that or push it too far. And so these are all good information, especially in the process of PCB design. And a lot of times, especially like the TI data sheets, they actually provide you an example layout of how this might look like whenever you're laying it out and designing a circuit. And then you can scroll down. And so the order of this kind of changes depending on what manufacturer it is. But then you see here towards the end in the TI data sheet, the layout guidelines. So if there's any specific guidelines, it's important to know. Some circuit elements and ICs might be sensitive to noise. And so you might want to not have certain ground planes underneath it or something like this. This one specifies that they do want a ground plane on the bottom layer because it helps provide better noise immunity and signal integrity. So we're going to want to make sure to abide by what the data sheet recommends, which means that we do want to check the data sheet. The data sheet will become your best friend. And so then another thing here is that the data sheet also includes what the package looks like, which might be helpful if the KiCAD libraries don't have what it looks like in real life. And so this is what you call the footprint of the symbol. And so what we had above here is a symbol, kind of. You just have a high level of what it looks like with just its pin connections. And then you actually have what it looks like on a PCB, which is this. So whenever if you ever have to make your own footprint, which is what this is called, you can just go to the data sheet and they'll likely include some land pattern example. So then it tells you the exact dimensions of what each of the paths need to be. And so that's how you go about doing that. But for this circuit, we don't actually have to look through too much of it because they do provide us with a working circuit schematic that we can just go off of. But that's good to know if you ever have to design your own schematic. So then let's first look up the 555 timer. And so we'll go ahead and include this. And so then it has this. And so then once you select it, you could just click OK. And then you could place it anywhere you would like. So I could just place it here. And now we place our first element here. So notice that the symbol doesn't necessarily match whatever this schematic here. So you have to be careful to make sure you're connecting to the right things, because notice on this right side, there's only pin 3 here, but here pin 3 is on the top. So you're going to be careful about what you're doing here. And so now what we can do is start laying out some of the other components as well. So we can do that by navigating over to the op-amp again, and then just selecting anywhere. And so let's say we want to add a 1K resistor. So we can look up resistor R, just click the one that says R is generally just the general resistor. So we'll go ahead and click that. And then we'll place it here. And so that one, this R, what they call R1 here, it goes between 7 and 4. So for here, we can just place it here. And then we can add another resistor. And so then we just go here. And then notice it's in recently used, which is convenient for us. And then that one's between 7 and 2. So we can just put this right here for now. And then we can always move it around to make it more neat later on. And then we can add another resistor that goes between 3 and ground. Put it here for now. And then we want to add some capacitors as well. So capacitors, you go and get the capacitors, and it's just labeled under C. And notice that one of them is a ceramic capacitor, one is an electrolytic capacitor. If the electrolytic capacitor that you use ends up being a polarized capacitor, which I believe a lot of electrolytic capacitors are polarized, we do want to make a differentiation between the two, so that way we don't accidentally get a non-polarized one in there. And so this one goes between 5 and ground. And then if we looked up C again, and then we can actually look up polarized capacitor, which is CP, and then we can just place it right here. And so now we have all the components that were there from the original schematic here. And so notice that we can move it around still, and there's certain keyboard shortcuts that you'll become very familiar with as you start to use KiCAD a lot. So then before we start moving things around though, let's go ahead and indicate power. And so power is important because you want to make sure that ground obviously isn't connected to power and different powers aren't connected to power. You want to make sure that that's clearly differentiated. And another important part of schematics is that it's almost like a document to show this is what your circuit does. So it's important to specify exactly what power it is expecting. So you go ahead and click the ground symbol, click anywhere, and then you get to choose your power symbol. For this one, we'll choose ground first. And there's different kinds of ground. There's the analog ground and digital ground, things like that. A lot of times we'll use just the normal ground unless we're isolating grounds. So we'll just go ahead and place this here. And then we want 9 volts because that's what they specify. And then we'll go ahead and look up 9 volts. And then go ahead and place it at the top here. Okay, so now we have everything that the schematic originally had. And so now what we want to do is we want to actually connect the dots essentially. And so in order to connect the dots, to lay out those connections that this schematic had, go ahead and navigate to this right taskbar again and click place wire. So whenever you're placing a wire, you kind of want to go from dot to dot, but know that you don't actually have to try to do it directly, and in the sense that you can shape the wire to be what you want it to be. So in this case, it's just most practical to go a straight line. And so you connect the two dots. Notice that the two dots that were there disappear. It goes from here, and then the dots disappear, which means that you laid a proper connection. Now, you might wonder, why don't we just place this ground here up here? Well, this is possible to do, but I know KiCAD is sometimes a little buggy. So I would always place like a wire between things because that makes it explicit as well that it's supposed to be connected there. And so we're going to go ahead and lay out the traces. And one important skill that might, or keyboard shortcut that's good to know is if you hover over anything, press M, then you can start moving it, press escape to just go back to where it used to be. And then if you hover over anything and then press R, then you're rotating it. And so those are good things to know when you're trying to move things around to make it as neat as possible. So we could go ahead and lay out the traces now. And so I'm going to move brown to be a little right here. And so when you're laying out the traces, an important thing is you want to make it as neat as possible, because neatness and readability is very important in schematics, because the schematic is not just for your present self to make the PCB, it's also for other people to refer to in your PCB, so that way they can see what your PCB is doing and what's happening, and also for your future self if you have to go back and look back on it. So these are all good things to know. So then another thing is we have this capacitor, and it goes, one of them goes from 2 and 6 to ground here. And that's the polarized. So we'll just go ahead and connect it here. And then notice that if we want to do a straight line here, we don't want this. So we'll actually go it and then click there. And so that way it's there. And then just for readability, you can hover over anything and press D or delete to delete it, not D. And so then we can kind of make this a little more central. And then go ahead and connect the dots to finish it here. So notice 2 is supposed to be connected to 6, but we'll come back on a way to actually make this easier to do, because notice that this might be a little messy. Like notice that this trace travels such a long distance away, and if there's too much overlapping traces, it can get confusing and hard to read, which defeats the purpose of what we want the schematic to do. So we'll get back on maybe a different way to go about doing that. So then finishing some of the connections here, this capacitor goes from C down to ground here. And then we have this resistor that's going from one of them goes from 7 all the way to 2. And so 2 as well as 6. So we can actually just connect it directly to 6 here. And then we'll show the way to connect it that is better than actually just drawing a trace here. Though in this case, since it is a fairly simplistic circuit, then you might not have to worry about it as much. And then this resistor here, you can place this, move this higher because it goes from 7 up to the 9-volt source. And so notice that now, okay, ideally we would want to place this here, but that covers the symbol. So what we can do is actually move this here to be somewhere where it's not actually in the way of something. We want to avoid too many things overlapping, because then we can't read it, and then that's not good for a schematic. Go ahead and lay it out here. And so now we have 9 volts there, and then we have the resistor that's connecting 7 to 9 volts here. And then this also is connected to 9 volts. So we can go ahead and connect 4 to 9 volts as well. And then we have this resistor here. We're just going from 3 to ground. So it might actually be easier if we move this one here. And go ahead and delete these now. and then actually lay out this resistor first. Actually, move that back. Okay, so then we have 3 connected here. And then we also still need that diode. So then we'll go to the op amp symbol or get that LED. So then you can just look up LED. So we have our LED here. The position matters. So then we can rotate it pressing R. And then we have this here. And then this is connected to ground right here. So not the complete neatest, but it's fairly neat. You can follow along with the traces. And then if you remember there, I omitted that one trace, and this was from 6 to 2, because those are kind of far apart from each other. And then we would have to create even more looping, and notice how now, okay, things are starting to get a bit messy. There's a lot of things going on. And so how do we go about fixing that? Well, what we can do is that KiCAD provides something called labels. And if we click here, we can actually place something called a label, which basically tells KiCAD, hey, we didn't actually connect the trace between here, but we wanted to, and we intended to. So there's actually supposed to be a trace between these two things. Go ahead and connect them or treat them like there is a trace between the two things or a wire between the two things. So how do we go about doing that? Well, we can call this here. Let's just call it THR, because that's pin 6 name. And so, and then this is what the label looks like. Go ahead and just place it anywhere on there. And so now we have this. Now, how do we tell it that it's supposed to be connected to 2? Well, we can just create another label with the same exact name. We want to make sure that it is the same name, and then go ahead and click it here, and then click it on 2, the wire connecting to 2. So now KiCAD sees this as equivalent to actually just directly connecting the 2 like that. But since that starts to make it pretty messy, we can just quickly do this way and say that this is supposed to be connected to this. So KiCAD sees that as equivalent to each other. So then just double checking that we do have the appropriate connections. We have 4 and 8 connected to 9 volts, 9 volts connected to this resistor here, and that's connected to 7, which is connected to 6. 6 is connected to pin 2 through the label, and then you have that polarized capacitor and ground. You have pin 1 connected directly to ground, 5 connected to the capacitor, which is connected to ground, and then 3, which is connected through a resistor, through a diode to ground. And so we have a circuit schematic that is equivalent to what this LED flasher is supposed to do. So now, okay, what are ways that we can improve the schematic? Well, it'll be good to include the schematic values or the actual values of each of the resistors and the capacitors. So how do we go about doing that? Well, if you hover over any of these components, so let's go ahead and click R here. We can hover over it and press E. Then it opens the symbol properties. And notice that there's 4 different properties that are kind of inherent. You can add more properties if you want, but we just kind of keep with what they provide us. And so there's the reference. And I would always leave the reference alone unless you want to name it something specific. But the reference is R, which stands for resistor, and then a question mark. So we're going to go through a step that's called annotating. And what annotating does is that it gives a unique number to each of the resistors and each of the capacitors. And so here, we'll let the annotation tool do that work for us. We'll just leave it as a question mark because it'll go in and then it'll give it a unique number whenever the time comes. So then what we're going to do is actually change the value here, and we'll just say 1K. You can write 1 kilo ohm, but since it's a resistor, the ohm is kind of redundant. So then a lot of times in our circuits, we like to use 0805 SMD resistors, which are its footprint, what its real life equivalent is. Footprint. So one way to actually label and give a footprint to each thing is to just do it each individually. If you click this little library thing, then it opens a window where the footprint library browser. Sometimes it can take a little while to load, so you just kind of give it some time. And so then you can scroll down to SMD or resistor underscore SMD. And SMD stands for service mount, THD stands for through hole. So notice that through hole elements have this like yellow circle, which indicates that it's going from the front side to the back side. This will make more sense when we go over the PCB, but through hole is exactly what it sounds like. There's an it's creating an actual hole on the PCB. Service mount is you have a different looking pad. Instead of the yellow circle, you have just this red rectangle. And that means that it's just going to be on one side of the PCB. So it's surface mount, it's not going through the hole. So that's kind of the intuition for where the name comes from. So we want to give it the resistor that we often use, the footprint that we often use, which is the 0805 2012 metric, which is located right here. There's two types. There's the hand solderable version, which is supposed to be easier to solder, but we will stick with just the normal 0805 2012 metric. And so you could double click it, then notice that it populates the footprint here. So now we added the value, we added the footprint. There's actually another way if you just want to give all the footprints at the end where you can do it, and I'll show you at the end. I just wanted to show that you can do it each individually if you would like to. So then once you're okay with these, then you press OK. Notice that R becomes 1 kilo ohm, and then it's just our question mark still, which we want to leave alone. And so then we're going to go ahead and give values to each of these resistors. So this resistor is the one connecting 7 and 9 volts, which is a 1 kilo ohm resistor. And so for now, so I can show you the other way to assign footprints, I'm not going to actually assign a footprint to each of these symbols. I'm going to save that for the end. So this one's 1K, and then the next one is connecting 7 to 6, and this is going to be 10K. So I'll hover over, press E, and then 10K. And this capacitor is 0.01 U. Then this capacitor here is 10 U. So now all the resistors and capacitors have the value that it's supposed to have. And notice that one thing is we don't want too much the traces going through it or other components. Like we wouldn't want this resistor to be like right here. We want to make sure that they're spaced out well enough that you can read each thing you want to read. And so then the last thing we want to do is, before we move on to the next step, is we want to actually give this diode a value. Why? Because diodes often, especially in our circuits, actually have some kind of value or meaning to it. Either it's a power indicator or some indication that an error light or something like that. So we want to indicate, like, we don't have LEDs for no reason. So we want to indicate what it means. So, or what the LED stands for. In this case, it's just a flashing circuit. So we can just write flash there. And so then now we have a circuit schematic that matches the schematic that we have here. So let's say now that there's a few other functions before I move on, because we accomplish our task in laying out the circuit that we wanted to. And we could just move on, but there's a few other, I guess, functions that KiCAD offers that I would like to show before we move on to the next step. Okay, so next thing is, this one is helpful whenever you want to have a no connection flag. So let's say we weren't using one of these pins. KiCAD gets mad at you whenever you run the electrical rules checker, which we'll talk about soon. It gets mad at you if you don't place no connection flags where there's no connection. That's basically telling KiCAD, hey, we actually intend this to have nothing connected to it. And so we want to keep it like that. Then another thing that we might use is, especially for more complicated circuits, let's say this circuit was just like a small circuit in a circuit schematic that is much more complicated than this. then what would we want to do? Well, okay, imagine if there was like, we needed 10 of these for some whatever reason. Well, then that kind of starts to get a little chaotic and hard to read because there's so much going on. So what we can do is create something known as a hierarchical sheet. And so we'll just place it here. And then notice here. So what are you doing when you're creating a hierarchical sheet? Is what you're doing is you're creating another schematic file and then linking it to this one here. So let's just call this one test here. And then test here. Okay, so then when you go into it, now you have test. And so let's actually, and then if you do Alt back, and you go back. So let's actually make a use for this. So let's create another schematic file. Let's say we have some kind of, so in this schematic, we would just include it onto this, but just for the sake of showing this demo here, let's say that we have a circuit, another PCB that's sniffing this one and seeing when is the LED on, when is the LED off. So we're going to want to kind of send like some voltage measurements to it. So we're going to want to send what this Q is here and then what this ground is here. So we want to lay out some kind of connection to that. And let's say we wanted to put that connection for whatever reason on a its own hierarchical sheet. So let's call this here. And then let's just call this output. And it's good to have somewhat informative names for these sheets. Okay, so now we have a sheet and that's called output. And so notice when you double click it, it opens a new schematic file titled output, but it's linked to the previous one. Okay, so here, what we're going to want to do is we're going to want to lay out a connector. So we go ahead and click the op amp. So for us, we use general connectors. So notice that there's female and male. We just want the generic one. So go ahead and just type however many pins. So the first one's the number of rows. The second one's the number of pins. And notice that the connector generic comes up and we're just going to go ahead and click that and then place it. So now we have a generic connector here. And so now what are we going to want to do? Well, we want this to connect to something in the sheet that's above it in the hierarchy. So how do we do that? Well, let's go ahead and lay out the traces so that way we can connect here. And then we do that by clicking place a hierarchical label. So what this is saying is that this signal here, this point here, needs to be connected to something that's on a different hierarchical sheet. So that's what we're doing by there. And so this one is going to be an input to this hierarchical sheet. So we're just going to call this light on or light. And then we'll call this one bottom one here ground. And notice that you can change the orientation and also the shape, but we know this is going to be input, so we're going to stick with that. So now we're saying that those two pins are coming from somewhere external from this hierarchical sheet. So we laid out one connection point there. How do we lay it out on the other end? So go ahead and alt back into here. So then let's go ahead and zoom into this hierarchical sheet connection. So if you go ahead and click this button here with the little turquoise arrow and click on it, notice that light shows up here, and it's gonna allow us to import essentially all those hierarchical labels from that other hierarchical sheet and basically put it into this into this sheet here. So we have this here, we have light, and then we have ground. Notice that if we try to select another one, then it gets mad at you because we didn't have any other hierarchical labels. So we're not quite done yet. So now we kind of have the starting point and we have part of the connection made, but we still need to make this into this circuit here. So what we can do, we can lay out traces here. So the good thing is that power labels technically are you could think of them as global variables. So whatever hierarchical sheet you're in, you put a ground symbol there, it's still connected to this ground. So that's another thing that we could have done instead of just doing what we're doing here. But for the sake of showing it the way this way, we'll go ahead and then use that label tool that we used before, saying that this is supposed to be connected to light and this is supposed to be connected to ground. And then we say that this is the signal or the part of the circuit that we mean by light. So we want this to be sent. So it's these two as being connected together. And then we want this part to be what's considered ground. We'll go ahead and place it here. So now we've successfully linked the things inside this hierarchical sheet externally to the ones here. One other thing is we do want to label this connector here to be some kind of valuable, useful meaning instead of just con 0102. This connector is obviously connecting to something else. So we can just say this is maybe a light connector, like, and then go ahead and press the OK. And so now we have this. So now we kind of learn what hierarchical sheets are, and that, let's say we want to say some text. So the data sheet was pretty clear. They want this one to be an electrolytic capacitor and then this one to be a ceramic capacitor. What do we do whenever we want to actually specify that that is indeed the case whenever we're laying this out? So go ahead to the right taskbar and press T, that stands for text, and then go ahead and say we want this one to be an electrolytic capacitor. And so then let's go ahead and edit it. And so then place this. Let's see, we can make it right. And then place it right with that capacitor here. And then let's do this one here to be ceramic capacitor. And place this here. So now we laid text, we kind of gave some notes here that might be useful for other people to see. And sometimes this even means like you can say what this circuit actually does, because sometimes the circuit decisions that you make isn't necessarily one that's immediately obvious. So it's good to write that somewhere so that way future generations can also see that and understand what you intended to do. And so those are some of the useful functions that we use with the schematic tool. And so now let's go about, okay, we laid out everything that we want to include on the schematic. What do we do next? Well, we want to annotate it, give it each component a unique name. And so how do you do that? Well, you click this little button here and say annotate schematic. I go ahead and just leave everything as it is. If you end up adding more parts to it in the future, like let's say you forgot another component or something like that, then just go ahead and re-annotate it. It keeps all the existing annotations. You could reset it if you want to, but it's good to just do that. And then annotate, it says that it annotate, and then close. And so now notice that instead of having question marks, each resistor has a unique number and each capacitor has a unique number. And so essentially we're naming them when we do an annotation. We're giving them a unique identifier. So that way, whenever we see them eventually on the PCB, we know that's what that meant. And so now we annotated it. And now the last thing we want to do before moving on to the PCB stage is to actually verify that it makes sense, but we also want to finish laying out the footprints. So before that, let's go ahead and load the footprint libraries. This step always inevitably takes a little while. It loads a lot of the footprint libraries, but this allows us to assign all the footprints all at once, which might be quicker than trying to do each individually. Because you want to make sure that each of your components actually has a footprint, because you're telling KiCAD this is what it looks like in real life. So if it doesn't have a footprint, then KiCAD won't know what you meant by it. Okay, so notice that now you have a list of all the components that you had. So with the capacitor, this 10U is going to be an electrolytic capacitor. So electrolytic capacitors tend to be let's see, one of these here. So let's just go ahead and you would want to have a part in mind. So if you want, we can even like go to Mouser, which is where we order a lot of our parts, and say electrolytic capacitor. So we have an idea of what you want to know. And in this stage, it's also kind of good to make a cart if you're a Mouser cart, or have an idea, because by this point you would have an idea of what each one would look like. And so then you kind of have, you would want to populate a cart so that way you know, okay, this is what you want to see. So let's say we, and Mouser's nice, so you can eventually, okay, so let's say we want a radial leaded or radial leaded one, so it opens it up, and then you could choose the capacitance value. So we actually want 10U. And then we can actually apply filters here. And so this is always a good step to do, because you want to know that there exists a part that is useful for us. And so notice that these have sizes, and you can see here, you can say we wanted this one. This is a radial one, so it's going to be somewhere here. And then it tells you kind of the diameter and then height and things like that. So you can see here, it kind of gives us, okay, diameter 6.33, 6.3. So we could go with one of these here. And let's just, for the sake of time, go ahead and select this one. And so then we can continue here. Okay, notice that you only double click. Now C1 now has a footprint associated with it. C2 is the ceramic capacitor, so we'll use the SMD one here. And we also use the 0805 metric here. So we'll just go ahead and click that. The LED, we also use 0805 LEDs. So we go to diode SMD, look for D0805. And then for connector, a lot of our connectors also tend to be Molex microfit connectors. So we'll go ahead and navigate to connector underscore Molex, and then we'll look for microfit 3.0 and look for a 1x2. For this one, let's say we wanted it to be a vertical connector. So we'll go ahead and select that. And then we go back to populating the resistors. And so then we get 0805, 0805, and then, okay, what package do we want for this? Notice that sometimes the things that KiCAD provides the packages, but in this case, it does not. So let's say we want, okay, so we can see the different packages it has here. This one is I think this is a VSS. Or this is one of them. Then you have one that's actually like the dip ones that actually is through hole, and then you have the SOIC. So we'll go ahead and stick with the SOIC one. So if you scroll down and look at package, and then you see SO, you can find it here as well. So SOIC, and then we can go ahead. We don't need a thermal pad for this one, so we'll go ahead and just select the SOIC _8. There are different versions of it, so you actually want to make sure that you select the right one. And then you would, I think these all have thermal pads, things like that. So go ahead and just select this. Select the generic one here. Okay, so now we have that for this one here. And so notice that we gave footprints to each one of them here. So then we want to apply save schematic and continue, and then click OK. So an interesting thing with the SOIC and all those things is that a lot of ICs tend to be one of those common shapes. So then you can a lot of times find the footprint on KiCAD rather than having to make your own. Okay, so now the last step before we want to move on is we can perform an electrical rules check. And so that makes sure that things are correct. Now, this isn't foolproof, and there's some things that it sees as warnings that really aren't a big deal, but it's always a good practice to do that just in case. And so this is actually one of the most common warnings that come up. And so what does it mean? Well, it sees that there's power, and it sees that it's not getting power from anywhere. So we would be providing this power. In this case, it does bring up a good point on where we're getting this power, because we didn't include a power connector. But we can just go ahead and actually go ahead. Let's say we did want to have a power connector just for the sake of completeness here. And so we can just have a connector here, and we can label it power. Power. And so one shortcut that I like to do, so I don't have to keep clicking these, is you could always just copy and paste symbols that you used before. Same with ground. And so now we have a connection to power. So KiCAD is still gonna see this as not being driven by any other pin. So how do we go ahead and fix that? Well, if you click the power symbol and then do power or PWR flag, this is the way to tell KiCAD, hey, we're actually going to power this, don't worry about it. And so we can go ahead and just connect it here. I'm going to rotate it so that way it's connected there, and then just copy this one and then paste it. So that's here. Notice though that this one didn't have its circle created, which means that it wasn't properly connected, but now we're good there. So then we can go ahead and save it, which you should always be saving as you go. KiCAD doesn't crash often, but when it does, it doesn't save what you worked on. And so I think a lot of people have been the victim of that. So make sure to save it. It kind of sucks. And so now when we run it, notice that, okay, and notice that there's an item not annotated, which we haven't annotated this one yet. So we can just go and update the annotation, then close it here. And then we can give it a footprint here. Individually, there's no need to open it, the other one, because we already labeled everything else. And so now we can find Monk's microfit 1x2. Oh, that's mini fit. Microfit. Then the 1x2. We'll go use the vertical one and go, okay. So now let's give this another try and then run again. Notice that those warnings disappeared. So at this stage, we would, if this was actually a circuit that would go in the car, we'll do some verification, make sure that everyone's happy with it before moving on to the PCB stage. But for now, we're good with this. And so now we have a complete schematic, which I'm going to go ahead and make more centered. But now we have a complete schematic of what we want the circuit to look like. So let's go back to the presentation now. Okay. So some good tips that considerations to make while making the schematic. Like I said, organization and neatness is key. Readability is very important, and you may want to even separate your schematic into logical blocks using those hierarchical sheets just to make it organized, and so things functionally make sense as well. You want to double check for correctness. If it's wrong in the schematic, it will be wrong in the PCB because the PCB is based on those connections. Label, leave notes. Other people will read it. You want other people to understand it. And then always check datasheet for any recommended schematic layouts, i.e. some ICs require bypass capacitors. Make sure you include those as well. So bypass capacitors are capacitors that are between its power rails, so power and ground. And so it kind of smooths it out, the noise going into that out. Okay, so now we have the schematic done. Now let's go on to the PCB layout part. And I always like to call that kind of like a circuit art kind of stage because everyone kind of has their own style in doing it. And so there's certain practices that are universal and are more strict about it, but a lot of it is very much up to your own creativity. And so there's some logical thought that goes into it, but there's also some creative thought that comes into it. So we'll go on to some background information on PCBs. Okay, so PCBs have different layers. And so initially you can see here at the middle part here, we have this thing called a substrate, and that's the base material or substrate. It's usually fiberglass. You don't really have to know what it's made out of to do PCB design though. And then flexible PCBs actually use something else like a flexible high temperature plastic. Yes, and there is flexible PCBs, which that's kind of cool. And so then the next one here is copper. And notice that copper is at both the top part and the bottom part here, because this indicates that this is kind of like a 2-layer PCB. You have things that you can put here. Yeah, things that can look here. And so it's a thin copper foil, which is laminated to the board with like some heat or adhesive. So the number of copper layers is the number of layers that they say a board is. And we'll almost always use 2-layer boards. We don't usually need any more than that. And 2-layer board means that there's a layer on the front or in the back, nothing in the middle. It can vary in thickness and it's measured by weight in ounces per square foot. And so copper is where actually all those metal connections are going to be located, is in that layer. So then the next layer here, it's super thin, but it's that green layer right on top of the red, is called the solder mask. And it's the layer that really gives the PCB its color. And oftentimes you see it like iconically as green. And so it's placed on top of the copper layer and it kind of insulates those copper traces to make sure that you don't accidentally short anything while you're soldering or make any contact with anything. And it kind of also helps you solder to correct places and prevent solder jumps. Like imagine if the whole thing was metal and you're trying to solder it, it would be very hard for it to just not want to connect everything. So it's both insulating and helps you as well. So then the last stage in the cell white here is called the silk screen layer, and that's placed on top of the solder mask. And that's where all the text goes, the letters, numbers, symbols, anything that just helps it easier to assemble. You'll see, and when we go to the PCB stage, that like R1 has an R1 label to it. So we know that that set of pads corresponds to R1. And it's usually white, but can really be any color. And so this is some background information on just the layers of a PCB. Now, when you open KiCAD's PCB, you're going to have something called the layers manager. And I know this seems like it's kind of overwhelming, so I'm going to go over what each of it is, but really a lot of these you won't really be using. So I'll describe what each one of them is, but a lot of it isn't really pertinent to what we need to do. But notice that there's an F and B. So F stands for front, B stands for back. Then you have FCU or BCU. Those are just copper layers. So the copper layers that correspond to the copper here. And then you have adhesive, which is just the glue areas, and paste, which are the parts that will cover in solder paste. You don't have to worry about those. Those have to do when you have like reflow soldering and things like that. And same with mask and things like that. So we don't do reflow soldering, so you don't have to worry about that. Then the next one is the silk screen layer. So F silk, B silk, that corresponds to the silk screen layer here. And then you have drawings user, comments user. So those are actually just user drawings and comments that are more notational in aspect. You won't see it actually printed on the PCB. Eco 1, Eco 2, they're just layers with no purpose. I guess it's whatever purpose you want to make it. And then edge cuts are the final board shape or outline. Then you have this margin layer, and that's the margin relative to the edge cut. And then you have this courtyard layer, and the courtyard area is essentially, it's KiCAD's way of telling, like checking like, hey, this symbol is a lot wider than what its pads make it look like. So don't place any components near it, essentially. It makes sure that each component has a certain courtyard and that no other component goes in that courtyard, because yes, we're working with something that's 2-dimensional on a screen, but in real life it's going to be something that's 3-dimensional. It has height to it, and might have greater width than its pad suggests and things like that. So it kind of allows KiCAD to check whenever you run the design rules checker to make sure that things aren't crossing its courtyard. And then the fab layers are documentation layers. So what are layers that you actually see on the board? Copper layers, So on actual PCB, you'll see the copper layers. You'll see the silk screen as actual text. And then the edge cuts are the layers. Everything else you don't technically see on the PCB once you print it. So then you have that. So those are the layers on KiCAD. So what's the general process for PCB layout? This really varies per person. So ultimately do what works best for you. But generally what people say, so first you want to place your components in a way that makes sense. And once you've placed your components, then you want to lay out the traces, you want to connect them. And if you need to rearrange, you rearrange as necessary. And then you tend to want to lay out the copper pores or ground planes towards the beginning. And I'll show you how to do that and what that entails. And then you also want to lay out the edge cuts. The edge cuts can be done at the beginning or the end. It really just depends on if you have a strict size or shape that you want to fit this in, then doing the edge cuts at the beginning is better. So that way you can make sure that it's going to be that size or shape. It won't be bigger or won't be a different shape. But if you have a flexibility, you can always just do the edge cuts at the end if it doesn't matter. So now we'll go on to making that PCB on KiCAD. So we want to import this into the PCB file. So how do we do this? Now we go to this button here and it links us to the PCB file that you created. And so this actually allows us to, they call it forward annotate and back annotate with the schematic, which is why it's important whenever you open a KiCAD file to open it from this project file, because then it opens everything else that it needs. Or it makes sure it's linked. So then in order to import everything, we go ahead and click this and then notice that we can just keep everything as we needed. And then we update PCB and notice that now we have parts here. And so we could just go ahead and place it down. Okay, so when we first see this, a lot of things are going on. It's kind of hard to see what's going on. What do we actually need to see and things like that. So one thing that I like to do is turn off the courtyard layers, which you kind of see those as the rectangles surrounding things. I like to turn off the courtyard areas because as long as you don't place the components too close, it shouldn't usually be an issue. And then I'll also turn off the fab layers, which are just documentation notes. And so now it's cleaner to see. So what are all these white lines? And so these are something that's called rat's nest. And basically it's just KiCAD's way of telling you these two things need to be connected to each other. And when you connect something, then that rat's nest disappears. It just shows you that's what it needs to be connected to. But notice that this is not equivalent to saying, take this path. That line is just the path of like the shortest path. And so please don't follow exactly what the rat's nest tells you. Like you can already see here, if you want to connect these two the way the rat's nest says, it would go through a pad, and that's obviously not what we want. So we want to make sure that that's okay. So some important information to know as well is it tells you how many pads, how many vias you have. Vias are little holes that we'll talk more about it later. Tracks mechanisms, number of nodes, nets, and unrouted. And unrouted is an important one that you want to keep track of because it tells you want this ultimately when you're done to be 0. So if it's not 0, that means not everything's connected, so you still have work to do. Okay, so what are some baseline things? Well, you can always change your grid size. Let's say we want to do a grid size that's bigger. Notice that when we move down, you can kind of see the blockiness of it. It's not as smooth. Okay, let's say we wanted to make it smaller. Notice that when we move it, it's almost continuous. Oops. It's continuous. So you can change the grid size as needed. I'll go ahead and click it at 0.1 for now. Okay, so you can see that different items have different colors to it. And what does these mean? These correspond to the layers. And so you have J1 or this turquoise color, which is the silk screen. So it actually is printed on top of the thing. So one thing that I see a lot of people do is they place like a capacitor right here, or they have the copper overlap. Well, the copper is printed, and then we have that silk screen that's also printed on top of that. So then we have an overlap. We don't want overlap here because now when we solder it, we're like, okay, where's J1? Well, we can't see J1 because J1 is going to be underneath whatever capacitor is C2. So these labels are actually really useful and important for us because it tells us now, let's say we want to see what is C2? Is C2, which capacitor is it? Well, we can go to the schematic and see C2 is the ceramic capacitor, the 0.01 microfarad capacitor. And so we know what value it is. So when we're going to assemble it, we know what that is. So it's important for things not to be overlapping with each other. And so then you kind of see the difference between the through hole component and the surface mount component. Notice the through hole actually has a hole to the other side. And that's why it's in yellow, because it's an edge. You can see it kind of as like a cut. It's actually through the hole and through from the front side, back side. There's a connection on both the front side and the back side because it goes through it. But surface mount only has one connection, or it's only on one side. So it's flat on one side. So you can put something, one thing that it may not be immediately obvious. So if you click F, it moves it to the back side, or it's flipped, so you could change sides or something. Flip. You can literally put it right underneath it if you wanted to. That doesn't affect anything because one's on the front side, one's on the back side. They're not going to be connected to each other in any way because that the substrate layer and everything else in between are connected. So don't be afraid to move things on the backside for things to be overlapping on the backside if they're both surface mount components. That's okay. I know it's weird to think about because it is a two-dimensional space that we're trying to do something that's three-dimensional in, but we're allowed to do that. What are you not allowed to do? Well, we don't want to put this right here because that's an actual through hole component, which means there's a connection to the backside. So there's going to be a hole there where C2 would be. So we don't want that. And so I don't think I said this, but to move, it's the same keyboard shortcut. You just press M and it allows us to move. So now let's flip this back on the other side. Okay, so let's go ahead and let's go ahead and select, let me see. Okay, let's go ahead and start moving components around. So that way this rat's nest maybe looks and makes a little more sense. Okay, so we can go ahead and place this here. And this makes sense. We want the 9 volts to be similar to each other. Okay, notice that this needs to be connected to the other side as well. So maybe it makes sense to put R1 here. So I like keeping things symmetrical or like symmetrical as possible because it looks better that way. It's neater and it just makes our lives easier here. Okay, notice that this is on the back side. We can rotate this. Maybe we can go ahead and flip it on the back side. And just so that way we can show, we can literally just put it on the back side there. Where's D2 gonna go? Well, we have this here. It's connected to R. So let's see what R else is connected to. So we have it here. Okay, so then we generally want to place components close to what it's supposed to be connected to. But we don't want to place it so close because I mean, someone's gonna have to solder that. If it's like, they're not touching, it's okay. Well, someone's gonna have to solder that and try not to short those two pads together. So you want to place enough distance between everything to make sure that that's not going to happen. But at the same time, you don't want to place things so close to, so far apart that you're wasting space. So there's a fine line here. So one thing is, let's say I wanted to put this where this would allow for straight trace line, but it doesn't allow us to do that. Okay, so if we click here and hover over and press E, then we have edit properties of this, but we can see what a position is. And the position is really nice because rather than trying to count the dots on the grid or keep changing the grid size to get it exactly what you wanted, well, okay, that's annoying and it's hard to do. And I didn't know about this until later, so I was one of the people counting the grid sizes. It's not fun. So what are ways that we can just make sure that they will be aligned for sure? Well, we want, in this case, the y-axis to be same. So we can just copy and paste its y position, and then we can hover over R3 and edit it, and then we can update its y position to be this. And notice that this rat's nest is now a straight line, and it it looks nice and it works out that way. And so now we can do that here. And so we can rotate that. Rotating is just by R. And then we have this here. You just go ahead and connect that. So now we have those two components there. Let's see what R3 is supposed to be connected to. R3 is connected to this, these two paths here. So it makes sense to keep that there. Okay, and then if we wanted to, we can also find, let's pull up the calculator. Okay, so we have its Y position is this. So 107.265 plus, and then see what this one is. So we can take the average of the two and then just place the component between that. So 107.9. And then we can go ahead and place it that way there. Okay, so now we're getting close to connecting everything we want to. So, or placing everything where it makes sense to generally. So then, okay, so we have this here. So let's go ahead and make sense to, maybe let's place this capacitor right here. We want its x-axis to be aligned with this. So we could just go ahead. Oh, okay, so this one's annoying because sometimes their midpoints aren't exactly the midpoint of that. So what can we do? We can align it that way. And we can actually run the calculations if we wanted to. And so now this one is J2. This is this, so we'll go ahead and do it this way. So I think a lot of the times that it's good to do it this way. So I know it crosses it, but we would be able to fix it this way. We wanted the connectors on the front side. And we always put the connectors on the back side. The connectors are one of those things where you want to be careful about because there's an actual, we're actually connecting it to something else. So we want it to make sure that it's on the right side. We want to keep that in consideration. So now we kind of just initially laid out everything in a way that kind of makes sense. We can shift this over here. It makes sense well enough for us to start laying out the traces. So how do we go about doing that? Well, we go to this right side and we go click this trace. Okay, so then we want to connect things. And so it's similar where we just kind of connect the dots here. But almost all the time, what KiCAD provides you as its default path, like let's say, so this to this. Like, okay, that's not that bad of a trace, but there's certain other things that we always want to be careful about because sometimes the trace that it initially gives you isn't very good. So we do want to keep that in mind. So let's go ahead and lay a trace here. And so it goes straight there. And then these are connected together. And so I'll save brown for later, and I'll explain why soon. Okay, so then let's see. It makes sense to connect these two. Okay, so let me actually move this over to the right a little bit. And go ahead and keep. So then we try to make it kind of symmetrical. Okay, so now that works out. Okay, and so then we can connect these two. Okay, and then we can go ahead and connect this to light. And then let's go ahead and connect these two. I want to connect it here. So notice that this is very much not ideal. We don't want a trace to look like this at all. So what are ways that we can work around this? So now we have a conflict here. We don't it wants us to go around like this, and this is not ideal in any way. So how do we go about solving for this issue? Well, okay, here's what we do. One thing we could do is, let's say we want this to be connected here. Okay, so let's go ahead and lay out the trace here and then do this. Okay, now it wants us to go around here. That's not the best trace. We want to take a fairly direct path anywhere we go. And so what we're going to do is press V, and V means that we're laying a via. Notice that that's kind of close to that pad though. So what we can do is we can move these over slightly, and then we can allow it to finish its connection there. And then we can pick up where we left off. Okay, and so now it doesn't let us cross it. So then we want to get to the back side, and we want to basically make a hole to the other side. So that way we can lay the trace on the other side and then connect it to the trace on the other side. So basically just there's a trace here. We want to go under and then loop it there. And so how do we do that? If you press V here, then we lay out something that's known as a via. Then we keep going to the other side. And we can lay vias on other tracks. So we can just lay a via here and then connect it. So now we've connected it from the front side, and then we looped over to the back side. So now we have that. So notice that we can change which layer that we see first. Here, front side, back side, front side, backside. You can also change it here as well. So we also have this capacitor here. So we also do want this to be connected here, but notice that that's on the front side of it too. And so I'm going to play a via here. And sometimes notice like things aren't that ideal sometimes what KiCAD does. It's like not straight, which isn't always the best. You want to lay out via here. Notice that you can just redo that one. Via here. Okay, so we can lay out the trace here. And this. And then you can lay out a via here. That's going to connect to our track here. So now we have that. And so then we still have 9 unrooted things. We're going to avoid ground for now, and I'll explain why soon. Then we have THT. Let's go ahead and connect these two 9 volts together. But notice that once again, we have something that's creating a conflict. So what we're going to do is we're going to create a via. That takes us to the other side. Okay, so now we have that. And so now we have this connected to, and this one needs to be connected to this here. So what we can do is we can just go ahead, start laying out this trace here. Okay, and so one important thing that we didn't really consider here, because we don't have to worry about this, is that these trace widths need to be put into consideration. Like, okay, so this circuit, if a lot of current needs to run through it, then we need to consider what that entails for us, because some of these traces can only handle so much current. So we'll talk about this later, but there's a calculator that we can use to actually solve for it, to see what's the minimum trace width size, and then we can actually change it by either hovering over it and changing it, or just changing this track size that we used here. Okay, and so then let's go ahead and connect this to that here. Okay, so now we have that connection there. And so things slowly start to get pieced together. So notice that the only things that we still need to connect is now this 9 volts here, which will go around. Okay, and then we'll place a via here. Notice that we could put the back trace here because this is on the back side. And so there's no limitation on where this, there's nothing on the back side here. So we could just put the trace anywhere that doesn't conflict with anywhere on this back side. So we could do it like this here. Okay, and notice that since this is a through hole component, even though we moved on to the back side, this through hole component, you can connect it to the top from either the top side or the bottom side. So there's no need to create a via here because this is on the other side, on both sides already. So we can choose whether or not we want to connect it from the front side or the back side. So now we kind of have a lot of it laid out now. So what's one thing that, why was I holding off on these ground planes or these ground connections? Well, now one useful thing to do is we often lay out something called a field zone or a copper port, which basically that entire copper layer besides what the traces are is going to be a certain voltage level or certain signal. And we often label that to be ground. And why do we choose ground? Well, ground is chosen because it allows us to, it helps reduce noise, one, and then it ensures that each of these paths have a really short path to ground. They can fairly easily all connect to ground. All these ground connections can connect to ground, and then it enables it to be all ground because the traces have an inherent small amount of resistance to them. So we want all grounds to be as equal as possible. And by doing that copper pour, we're able to do that. And so let's go ahead and create that. And so what we're doing is we're just gonna lay out the copper pour here. I'm gonna actually make the grid size a little bigger so that way we can ensure we're making a straight line. I'll go ahead and do this. Okay, notice, let's go ahead and do one on the front layer and we can just do ground on both sides. And then also, if you remember from the data sheet, we do want ground on the back side because that's explicitly what the data sheet told us to do and that it's good for us to do. So we tend to change to solid and then we can just, okay. And now we just make a square. Or a rectangle. Okay, so notice that you lay the ground plane. There's different ways to actually view this. So I'm on this view here. The one that I tend to be on is this one here. And so now we have that. And then you can also do this side where it actually shows the pour. So notice that we went from 5 unrooted connections to 2, and which is why I was saving it for later, because now these are directly, like if you take this ground one here, why is it not connected to ground? Well, it's connected to the ground plane on the backside. So we don't have to worry about that anymore. And so that allows us to do that. And then let's also go ahead and create a ground plane for the top layer as well, using the same idea. Oops. And so you don't always have to do a ground plane on both the top and the bottom. But in this case, it was kind of nice to do a ground plane on top and bottom, because notice that all the ground connections disappear now. They're all connected to ground. Sometimes, a lot of the times actually, though, that's not going to be the case. And why is that? Well, sometimes you might create a signal island where there's like different traces going this way, this way, this way. So then essentially there's a pocket of the PCB that's not directly connected to ground. And so in that case, you might need to connect it to ground, certain ground pads this another way. But in this case, it worked out. We don't have to worry about it. Okay, so now we have this. Okay, so one thing is you can move the silkscreen text. I'm going to go ahead and move it to make the size more compact. Let me go ahead and change grid size back to 0.1. I think I often work in 0.1 because it gives you some flexibility without too much flexibility. And then let's go ahead, move C1. We could rotate it by pressing R and then just place it there. So notice now we kind of have a PCB. So let's say one thing that is good to do is sometimes it's good to view it on a 3D viewer while you're doing it. So this is what it kind of looks like in real life. This is what this schematic would look like. And notice that you have things on the back side, you have things on the front side, and you have it looking like this, and it doesn't look too bad. And so sometimes it's good to do that just to see what does it look like in real life. And it's good to have an idea of what the PCB would look like in real life, because it gives you an idea of what you can place on the back side, what you can place on the front side, and so on. And so you can see here, notice that that capacitor is directly below this resistor, but since they're surface mount components, they're not interfering with each other. But you can see the through hole components actually have a hole to the other side. So we kind of laid it out the way that we like it. And so let's say we're satisfied with this. One thing that's important to know is that if we move one of the components, let's say we move R2 for whatever reason, okay? So now you have those, it gets mad at you for that. But now if we open the 3D viewer, notice that that filled zone did not update. There's still the filled zone that it still matches what it was before. So in order to update it, we have to press B, and that updates the fill zone. So B as in boy, but I'm going to undo that and then press B again to update it. And so now we have a PCB that we're good with. And there, let's say in certain components, you might need to had a keep out layer. So, okay, let's say for whatever reason, maybe we had a component here and we want to do a keep out. We want to keep out track, keep out vias, and keep out proper pores. And a lot of times it's on both sides. So let's say we just had a little area that we want to make sure that there was no copper in. And so a lot of the cases, this might be like with certain ICs that specify that, or maybe even like a crystal oscillator, because it's very sensitive to other signals. So you don't want that to interfere. So notice that when we go to the 3D viewer, it still hasn't updated yet. So we want to press B. And so 3D up there. Notice that there's now the light green is that copper pour, the ground plane that we laid. But now on both sides, we have this like darker green rectangle, which is showing that that's a keep out area. So that area on the copper plane is not connected to ground. But that's not necessary for this circuit. And so what other things can we do with this? Well, okay, so one thing it do is we're not completely done with the circuit yet. If you recall from the layers discussion, we need to specify what the actual edges of the board is. When we do the 3D viewer, it kind of assumes what it thinks it's going to be. So how do we do that? Well, we want to navigate to the edge cuts layer, and then we want to draw a line. So now that's when we go here, and then we want to just draw a line. And essentially just you can follow the copper pore if you would like. You can make it a little bigger than the copper pore or smaller than the copper pore. The copper pore can actually be bigger than the dimensions of the board. It just assumes that it stops at the edge. Okay, so we have this. And then now we have our PCB, kind of. So now one thing though is that these points, those corners actually end up kind of getting, they're kind of pointy. So what we like to do is we like to create, let me make the grid size a little bigger. Okay, we like to create corners, rounded corners. So let's go ahead and do that. So what you do is you hit this arc button, and then I like to make sure that it's a square. So just make sure that it's even. You go in the same amount up and down, or so. And then sometimes it's a trial and error on which direction it goes in, because I often forget. But go ahead and then do that. I like to make it consistently the same round corner on all ends. Okay, so now we have that. Well, now we kind of define two edges. So what we want to do is actually, okay. Okay. Let's go ahead and we could go ahead. Let's actually undo the edge cuts, because this is one thing is it always prioritizes that copper plane. So sometimes it's a little annoying because you want to access the edge cuts, but it doesn't allow you to. So let's actually make it just slightly bigger so that way we can touch it. And so we'll just repeat what we just did here. And so you always want to make sure that these are straight though, because you don't want a rounded edge board. That would not be good. Or like a crooked edge or anything. You want to make sure they're straight. So sometimes a good way to do it is just by changing grid size to be bigger so you can't make as large of a step. Then we could go ahead and do this. So we're 4 down, 4 in. So we'll go do this to all 4 sides. All 4 corners, and now we're almost done again. Okay, and then we go ahead and move the edges back by selecting them and just connecting it to the corner, so that way it's not, we're not doubly defining what it should be. Okay, so now we have a PCB. And so now when we go to the 3D viewer, we're able to see that it updated the edge cuts to what we did. And you can kind of see, okay, it has the rounded corners that we want, kind of has the shape that we want. We still haven't updated the keep out zone, so that's a good thing. That's a good reason why to check the 3D viewer a lot, because you're able to see that if it hasn't been updated yet. So now it's been updated. And so you can kind of see this was what this would look like here. Okay, so now we're not quite done yet. So we laid out everything that's important, but we still want to make this usable too. Okay, so what does that mean? We want to label things, give things text, and we can even draw things if you want. And so let's go ahead and let's call this. Oh, okay, you want to make sure that you're on the right layer for this. So let's go to the silk screen layer and add some text and images and maybe something like that. So text, let's go ahead and say we want to call this a flashlight, flashing light, because that's what we called it. And you can go ahead and place the text. Oh, let's go ahead and change the grid size back to 0.1. So let's call it flash. You can even change the width, height, the thickness, and things like that. Let's go ahead and say that this is our flashing light LED. And so then That's what we have here. Okay, so let's call this block talk flashing light LHRS fall 2021. So a lot of times we will label our PCBs, and you might be able to say like, hey, like your name was here, or like in my case, like I can write Hannah was here. You can put like things that you want. So notice that this is kind of too big. So what happens if we move it to the next line? Okay, and we can fit it here. So it is okay for the text to cover over the copper trace, but we don't want it like here or anything like here, because then an actual part is going to be placed there. So it kind of defeats the purpose if it's underneath something, unless it's something that it's only meant for your eyes. So yeah, like you want to put all the official stuff where you can see it, but then you can have a little bit of fun with it where you can put something that no one else will see underneath a component. Like let's say we want to say solar is cool or something like that. We don't want other people to see that, but we can like put it underneath the component like that or something like that. So there's things that we can do with this that you can have fun with it. And then you can actually, once it's printed and done, you can like show it off to like recruiters and things like that. Like I made this PCB, which is kind of cool. And so let's say also you can have fun with like making drawings. So let's say we want a circle for whatever reason here. And so like maybe we want like a little circles or something. So you can draw what you want here. Let's say if we can have we can draw a little snowman if we wanted to. Things like that. So there's different things that you can do with this that you can have fun with. But with the official boards, you can just always put it underneath something. So you'll know it's there, but other people won't. And so now we kind of have that. Okay, so, and then when we look at the 3D viewer, you can see that now our text is there. And so it looks nice and looks cool. And so what's another thing that what's good to do is we also want to label these connections. It's like we don't want to accidentally put ground where 9 volts should be and 9 volts where ground should be, because then you just created a short. So let's go ahead and label what these connection points should be. And so this one has 2. So this one should have 2. Okay, so then we could go ahead and label what these are supposed to be, and then we can just do it the same way. Okay, so this is supposed to be 9 volts. So we go write this, and then we can write this is supposed to be 9 volts. And then this is supposed to be ground. So a lot of times it's good practice to do this because you want to make sure it's clear that what each connection is supposed to be connected to. So this is light. And you could just rotate it. So sometimes it's good to give a little bit of space leeway so that way it's not overcrowded or like the text isn't being covered by something else. But in this case, we have ample enough space to do that. So there's a lot of text going on, but we're able to see what it is here. And so then let's go ahead and a lot of times this is labeled, but here we want to, just in case, specify which sides the positive end. Like I said, you could put text on the copper traces and that's okay. So we can say with pins with polarized capacitors or anything that's polarized, you do want to specify in some way what's positive and negative. Here, the diode footprint symbol already shows what side is ground. And here the chip already shows what side is pin 1 because it has that line over it, all the other sides don't. So you'll see that there's certain kind of unique indicators like that to do that. Notice that you see a plus there, you see these here in the labels, and we are let's say we're fairly happy with this now. What are other tools that you can use when helping? Well, if you have a lot of things that you want to do, you can select it. And then let's say you need to align something. There are ways to do that. You could like align, distribute, and things like that. So instead of having to type a bunch of numbers, you could just like KiCAD do it for you. If you want to take a measurement between two things, let's say we want to know what the measurement is, we can use this ruler tool here that's on the bottom right here. And one thing that's good to do is to do dimensions, and we can do it in the comments user branch. So what we do is you get one edge, and then you get the other edge, and you pull out, and then you click. Okay, so we got, this one's 24 millimeters long. And so then we could do something similar here. And then this one's 26.5. And so we tend to like to keep the PCBs in metric because that's what we use it for here. And so you kind of see that that's the dimensions. And so you could save it. And the dimensions are good for the mechanical team. So that way they know what size PCB they're expecting for their enclosures and things like that. So now the last thing we can do is we can also run the DRC, which is the design rules checker. And notice that nothing happens. We don't have any problems or unconnected items. So we're good. And now let's say we're fairly happy with this design. So what do we move? And so before we move on to the next steps, let's go back to the presentation and see other things. Okay, so good practices for PCB layout. So any bypass capacitors, the capacitors connecting the that are recommended by a microcontroller and that connect power and ground should be placed as close to the microcontroller as possible because that's where it's most effective. The further it is, then it's not going to be that effective. And so neatness, organization, and symmetry are all really good things. Like it's not just being super strict or picky about it. They're actually helpful for us. It makes it easier to see what's going on in the PCB and also makes debugging easier when things are placed in a way that makes sense and that are clean and aesthetically pleasing. Like it's not just looks, it actually has a purpose. We want to make sure that there's no random trace appendages. So if you move an item, make sure to delete that trace. Like there shouldn't be just some trace that's hanging out that doesn't have a purpose. You want components to be aligned and parallel when possible. You don't want overlapping silkscreen text with the SMD pads or other silkscreen text. Silkscreen actually gets printed. They're helpful for us to know what is each component and what has text and things like that. One thing is avoiding 90 degrees angle, and I kind of include that with an asterisk because it's technically really not a problem for modern manufacturing techniques, but in general, it's a pretty good practice and it's important for really high speed and signal integrity. So I prefer no 90 degrees, but it's not a strict rule anymore. You want to label connections, circuit blocks, and LEDs, so like groups of components that may do something. You want to compact, but not too compact. You don't want to waste space, but you don't want to, at the same time, you want components and traces not to be placed so close together that it's going to be impossible to solder or their courtyard layers are overlapping. Adding a ground plane is always good. You want to round your edge cut corners and don't be afraid to add text and comments if needed. So while you're laying a PCB out, what do you think of? Well, you want to lay out trace widths. Those are always good. You want to make sure that the trace width can handle the expected current with ease. And so I included a link to the calculator here. And so you can say how much current you expected and how thick your board is. So let's say for whatever reason, we're expecting like 5 amps through something and the thickness is 1. Well, that means we use millimeters. That means the required trace width is at least 7.19 millimeters. And so we want to keep this in mind to make sure that our trace width is able to handle the current that it needs to. Other things is you want to check to make sure what is not allowed to have a ground plane underneath it. And so some things are like crystal oscillators that might be fairly sensitive to anything that the ground plane might have. You'll tend to see this on the data sheet. You want to think about grouping components based on functionality or what circuit block they're a part of. So think of the hierarchical sheets. Let's say if everything is in a hierarchical sheet, chances are they all have a similar function or they're working towards the same goal. So you might want to place all those components near each other. And you can even make a line on the silkscreen layer to block it off and say that this section is that. And I know the BPS leaderboard does that and the controls leaderboard does that. And so it makes sense also for them to be close together because those traces will be minimized there. And you want to also consider where the board is going to be mounted and placed in the car. Like, is there any space constraints? Is there any size constraints? Which side should have what? So if connections from one side are expected to come from one side of the PCB and not the other side, these are all considerations you want to keep in mind while laying out a PCB. So then laying out a PCB, especially for your first time, can be difficult. So some tips for that is think three-dimensionally. There's a backside for a reason. You understand what's through hole and what's surface mount, and think of the actual part. And if it's hard to visualize, check the 3D viewer. It will tell you, it'll be pretty obvious if you can place it on top of each other if you can't. So oftentimes the first design isn't always the best one. Feel free to move around things after you lay it out, delete traces, move things, keep trying again until it's a way that you like. So the trace that KiCAD automatically makes is usually almost all the time not the best. So move it around until you like it. And you can lay parts of the trace at a time. You don't have to just go from one end to the other immediately. You can lay it out this way and then lay it out this way. And then let's say you want to go lay it out. And then if you're having a hard time, some recommendations are sometimes it's good to have a top layer that's dedicated just to horizontal traces, bottom layers to vertical traces. And that way there won't be any trace conflicts essentially. And then change your grid size when needed, and generally just keep traces as short and direct as possible while still being neat. And so now I'll show how to make a Gerber file. Okay, so now you're done with this. How do we get what we can send to the PCB manufacturer and tell the PCB manufacturer, hey, this is the PCB that we want to design or want you to make. So what we want to do is do File and then go to Plot. And so it opens this here. So we want to label an output directory. And a lot of times what that is, it's you just want to create a folder within your bigger project folder and just call it Gerbers, and then just select that folder. And then you just want to say path relative yes. Okay, so generally you just want to keep all its default components, and then you also want to keep generate drill file. And then the thing is, you want the output folder to be the same as the Gerbers, but the important thing is PTH and NPTH in a single file must be checked. That should be checked. Make sure that's checked. So once that's good, then you generate drill file, you close, and you plot, and it tells you, and you close. And so now when you navigate to the file explorer, which you have to navigate to there. And so then notice that when we go to Gerbers, now it has all the Gerbers there. And so we're good. And so go ahead and save this, and go ahead and save this. So some other cool things to do is, since they're linked to each other, let's say you want this capacitor and you're like, where's this on the schematic? It highlights it for you as well. So they are linked together as well. And I don't know if it works the other way around, but I don't think it does. But that way you can see where it is on the schematic. Oh, actually it does work. So notice that R1 is highlighted and we're just playing around with R1. So cool things is, and that only works if you open them through the project file. So you want to make sure to do that. Okay, so now you have the Gerber files, and now you're good with this. So now we would send that to the PCB manufacturer. They'll be able to manufacture it, and then they'll send it to us. Okay, so because of how long everything was, we'll save the additional topics for another time. But if you have any questions after watching this, please message me anytime, and I'll get back to you, and we'll do that. And if you're interested in practicing everything you just saw, then you can go to Solar Vehicles team, the Google Drive, electrical team, battery, and then tutorials. And then there you'll see the presentation that we just used for this, where it has some of the links that you have. And the other thing is that you have an introductory KiCAD project that walks you through how to do things and kind of gives you a little more complicated circuit to work with, but it gives you a lot to practice your skills directly from what you just learned. So yeah, I think that's it from me. And if you have any questions, please feel free to let me know. I'll be happy to help. Thank you for watching.